Good morning, good afternoon, good evening, everybody. Thank you for joining me. My name is Prith Banergee. I'm Chief Technology Officer at Ansys. I joined the company about 3 years ago. Prior to Ansys, I used to be CTO at ABB and Schneider Electric. And before that, I spent about 20 years in academia. In my role, I'm responsible for setting the long-term technology strategy for the company, and that is what I'm going to talk to you today. Ansys works with customers in various verticals: automotive, aerospace, manufacturing, energy, and high tech. And we help our customers build the most amazing products using simulation. And so my talk is going to be on our strategy for simulation-based product innovation. Now, Ansys is a global simulation leader. We have been in the industry for more than 50 years. In fact, we started many years ago with the core technology of structural simulation using finite element methods. And then we acquired a lot of technologies in different physics areas over the years. For example, we acquired Fluent, which gave us fluid dynamics simulation capabilities. We acquired Ansoft to give us electromagnetic simulation capabilities. 3D Sim to get us 3D manufacturing capabilities. Granta to allow us to get materials manufacturing, materials intelligence capabilities. And our latest acquisition is Phoenix Integration, which allows us to move into the area of model-based systems engineering. We have also announced recently another acquisition that has not closed yet, called ZMax. In addition to these acquisitions, we also have been working with lots of partner companies such as Synopsys, PTC, Rockwell Automation, Autodesk, and Microsoft. We are a company of about $1.5 billion in revenue, $1.7 billion in revenue, and about 5,000 employees worldwide. So with this, where we have come is this product portfolio, which I want to share with you today. So at the bottom, you will see all our physics-based simulation capabilities. The world around us is governed by the laws of physics. And so we can model structural physics, we can model fluids physics, electronics physics, semiconductor physics, and so on. And we use different sort of numerical methods, some using finite volume, some use finite element methods, and so on. So at the core, we are a physics simulation company using numerical methods. On top of it, we have a set of software system simulation capabilities, such as digital twins, such as system software, embedded software, and safety analysis software like Medini. On top of that, we have recently acquired AGI, which gives us the capability to do digital missions engineering. We can simulate entire missions at very large scale, including aeroplanes and satellites and tankers and ships and so on. So really large scale simulation at scale. Then we go on the next level. We have a simulation platform where we can do material simulation, we can do various optimization, we can do process and data management, we can allow for multiphysics simulation, and all of these things run on high performance computing as well as on the cloud. We take these different software packages, and we have been recently working on different solutions such as autonomy, electrification, 5G, and IoT, which I'll mention in the next slide. And then we build these solutions in different verticals, such as aerospace and defense, automotive, energy, healthcare, and high tech. We are working today with more than 45,000 customers in these verticals. So I mentioned this different solution. Let me just deep down a little bit, right? In the industry today, we have, for example, the automotive industry is going through tremendous transformation, digital transformations with the use of electrification. So we have partnered with Volkswagen on a full electrification solution, which involves the design of batteries, battery cell packs, battery systems, power electronics to drive the batteries, the sort of the entire sort of fluid mechanics, the electric powertrain, and so on. So we have done a full electrification solution for our automotive customers, and we're also moving it to our aerospace customers. We have a full autonomous solution that we have partnered with BMW and other companies. And in there, we do different types of sensor simulation, like LiDAR sensors, camera sensors, infrared sensors, radar sensors, and so on. And we do scenario analysis, and then we integrate that with physics-based simulation to help our customers in doing essentially safe driving simulation, right? Where to certify a car for driving, you need to have almost 10 billion miles of driving. We can enable our customers to do that purely through simulation. We are also working on various 5G systems, working with the systems companies as well as chip companies, and also a lot of industrial IoT systems using digital twins and so on, which I will mention. Now, these are the products and solutions, but at the heart of it, there is a technology that drives these products. So as CTO, I am responsible for our long-term technology strategy, which is going to be the whole purpose of this talk. So at the core, all our solvers like Ansys Mechanical uses finite element analysis. Fluent uses finite volume methods. So these use numerical methods. So we are doing a lot of futuristic work on numerical methods. Some of these methods are direct methods, iterative methods, finite element, finite volume. Isogeometric analysis is a very, very new technique that we are working on called IGA. We're looking at implicit, explicit methods, and so on. So at the core of the core, we are doing a lot of work on numerical methods. And in each of these areas, we have centers of excellence that pulls in different engineers from different product businesses and into to collaborate and work together on these advanced directions. In addition to the solvers, we do pre-processing, and there's a lot of work that we do on meshing and geometry. So some of the areas we are working on in the future are conformal meshing, non-conformal meshing, morphing, parallel meshing, immersive methods, and so on. So a lot of work on pre-processing. The output of our solvers needs to be visualized, right? And today we visualize them on a 2D screen, but in the future, we are working on technologies to view our output on 3D using augmented reality, virtual reality, having purely immersive user experiences, and also working on safety critical HMI with, for example, for some of our automotive and aerospace customers. Our customers used to work with us on only single physics, but increasingly they need to work with us on multiphysics interactions, so fluid structure interactions or fluid structure electromagnetics interactions. And to support that, we are working on multiphysics, multi-domain, multi-scale simulations. And so we have a platform that allows us to do this using sort of weak interactions, medium interactions, strong interactions. We have a platform that allows our customers to do process integration and optimization, and I actually have a slide that goes into it. In the middle column, you see our work on AI machine learning. And there's a lot of work that we are doing in that area. And again, I have a set of slides that will talk about those methods to improve analysis productivity, to accelerate our simulation to what we call augmented simulation. We have methods using data-driven methods, physics-informed methods, and various sort of ML-based methods to do this. Then we do a lot of work on high-performance computing, which is essentially using parallel computing to drive a lot of work in this particular area, right? And we are looking at task-based parallelism, shared memory parallelism, message passing parallelism, GPU parallelism, and exascale computing. Again, I have a slide that goes into more detail. Now, many of these high-performance computing technologies run on on-premise clusters, but then increasingly the HPC capabilities are being available on the cloud. And so essentially what is going on is we are providing solutions for our customers on hybrid cloud, on-premise, private cloud, public clouds, and essentially moving in the area of what is called HPC as a service. The next areas that are model-based systems engineering. Increasingly, our customers do a lot of different specification of the systems at the high level using languages such as SysML. And what we are working on is collaborative architectural modeling technologies using SysML and essentially working with our customers to do what is called virtual validation and virtual verification and rapid prototyping. Very, very exciting areas. On the third column, you see work like digital twins, and we are essentially working on data analytics-based digital twins, physics-based digital twins, and hybrid digital twins. We are working on ICME, integrated computational materials engineering methods, and additive manufacturing methods. We are working on entire solutions, as I mentioned, on autonomy, electrification, and 5G. And finally, we are looking at a whole new vertical on healthcare. And essentially, the CT office is doing a lot of work on helping biopharma companies in their journey towards drug discovery. We are working on with medical device companies like pacemaker companies and so on, as well as medical equipment companies that build MRI machines and CT scanners. And finally, we are working on sort of clinical apps that essentially doctors and nurses can use in their hospital that will use Ansys solvers in the backend, but essentially provide it with a very simple sort of workflow. So this was a broad brush overview of the technology strategy. What I'll now do is to go into some specific areas for more detail. So the first area I'm going to talk about is AI machine learning. Now, AI machine learning is one of the most disruptive technologies that our sort of industry is seeing for a decade, right? I mean, it's, in fact, I was listening to a keynote presentation today by Sebastian Thrun, who is a very, very famous entrepreneur. And he basically said it is as significant as a printing press, right? So a lot of areas, a lot of industries are being disrupted by AI machine learning, such as recommendation engines and finding sort of pictures on images or videos or all kinds of technologies, chatbots and so on. We are looking at the use of AI machine learning applied to simulation. So within that, we have looked at different use cases like improving customer productivity, ease of use, improving simulation, augmented simulation, and so on, using for business intelligence and so on. So what we have done this year, and last year I kind of mentioned some of this broad-based work, but this year we are excited to talk about some of our work on AI/ML. And these things are happening not only by organic R&D with the teams within Ansys, but we are doing a lot of collaboration with our customers, we are with our partners, and as well as the universities. So we are working with universities such as Stanford University, Carnegie Mellon, MIT, Brown University, and others, as well as customers such as NVIDIA and partners such as Google and startup companies like Neural Concepts. And this is enabling us to essentially come with some AI and ML enabled products, such as hybrid digital twins, which I will talk about in the next slide, such as the hybrid ML solver, which is actually shown in this particular presentation, and ML for automatic setting of parameters in Ansys Discovery, resource estimates for Ansys mechanical solvers, fast thermal solvers, and advanced data analytics. So just to give you an example of how this ML methods work, right? In the flow solver case, I'm showing at the bottom a sort of a 2D image of a rectangle with a box and a hole in the middle. And we are trying to model the fluid flow over that yellow region. Now, to do this using normal numerical methods, using finite element methods, using Fluent, it would take, you have to break it up into small volumes and solve it with numerical methods. It would take a long time to do. Instead, what we do is you break this region into finer voxels, and each of these voxels, and you can think of it as in 3D, you do it in an 8 by 8 by 8 area in 3D. And in each of those sub-regions, you run sort of Fluent, right? And you get all possible solutions, right? But for a much smaller region and lower resolution. You take those solutions, fluid solutions, and use it to train AI ML models, those neural networks. Once you do this, those models are trained and those generate these different solutions. Then you enforce locally consistent solutions. Essentially, the neural networks learn from these detailed simulations, and then you abstract it to the entire problem. So this is at the high level how ML works. And what the top right is showing is some recent results. So for example, the left part is showing the results on Fluent, and the right part is showing the results on this using this ML-based solver. And something that takes Fluent, for this very simple case, 50 seconds, runs in 1.8 seconds. So a factor of 25 speed up. For larger problems, we have been looking some, for example, for external aerodynamics on a fluid flow over a car, these results in speed ups of more than 100 times. So very, very exciting area results in the area of AI ML. And this is going to be very, very disruptive to our industry. The second area is that of high performance computing. And our solvers like Fluent or Mechanical or Numerical or LS-DYNA, they all are using different forms of parallelism. At the highest level, they do what is called parallel parametric analysis, where you're doing multiple different independent problems, embarrassingly parallel. And essentially that is involving sort of job scheduling, HPC job scheduling, where you're trying to extract parallelism at the different level. Picture that you see on the left-hand side, you take that region and you break it up into different regions, as is being shown for the Fluent example, right? And then you do message passing to share information across those things. The next level, at each domain, you're using threaded parallelism, shared memory parallelism, right? That is using parallel tasks, parallel loops, and so on. That is where you leverage multi-cores and multi-threaded parallelism. At the finest grain, we use SIMD form of parallelism using GPUs and tensor processing units, TPUs. And we are essentially doing all forms of parallelism across all our solvers. So the top right is showing our results on Fluent. And this is by far the hardest problem to work on. Computational fluid dynamics using turbulence modeling is one of the hardest things to solve in industry. We have been able to apply this multi-level parallel approach to Fluent. And the picture is showing that it scales to 200,000 cores. This level scalability is unheard of in the industry, and it's very hard to do this, but we are able to do this because of the technologies that are shown on the top left. In addition to these core solvers, Fluent, Mechanical, LS-DYNA, and so on, that we have hand parallelized, right? But we started with a sequential algorithm and we did the parallel computing after. We have also got a brand new solver called Ansys Discovery, which was written from scratch to take advantage of GPUs, right? Using voxels and so on. And we started that with sort of mechanical solvers, then we did for fluid solver, then for electromagnetic solvers. So this is what is called real-time simulation. It runs natively on GPUs, but a single GPU. And you can essentially have Ansys Discovery running on a laptop, which has a GPU as an accelerator, right? And it runs really, really fast, but not as accurately as the core solvers like Fluent, Mechanical, and so on. But what we did is we took that core solver that we had for fluids in Discovery, and it says, well, what if you could take that core solver for GPUs and then use some of the domain decomposition methods. So using sort of MPI to share information across GPUs. So essentially we now have a multi-GPU solver for Fluent, right? Which is the latest result. I mean, essentially this is something that will be made available to customers in 2022 R1, right? It is a multi-GPU CFD. We have not seen anything like this in industry, very, very scalable speed ups. So the picture on the right is showing scalable speed up using cores. And now what we have is we have got speed ups on multi-GPUs getting tremendous speed ups. Next, let's talk about sort of hybrid digital twins, right? And this is the people have been working on digital twins for many, many years, right? You take an asset, you put some sensors on the asset, connect it to an IoT platform, and you can build digital twin sort of models out of the asset. While that is a very general approach, what we have done at Ansys is to do a simulation-based approach to digital twins. So we take those assets, we can run different simulators like Ansys Mechanical or Fluent or electromagnetics, right? The HFSS solver, and we can do a simulation model of that asset. The trouble with this detailed 3D simulation model is it takes a long time to run. So what we have done is we have got this technology for reduced order models or ROMs, and we have linear ROMs, nonlinear ROMs, static ROMs, dynamic ROMs, which is shown in the middle picture, right? And essentially use that to have these assets and run them much faster. And we essentially generate these models, call a twin deployer, to run this on the cloud or on the edge at the speed of that asset. Now, this is what is called a pure simulation-based digital twin. Most recently, what we have got is a hybrid digital twin, which I want to show sort of in detail in the next slide. So what this is showing is in the industry, people have done physics-based digital twins, as we have done. Other people have done AI or analytics or data analytics-based digital twins. What we have now shown is if you combine those methods using hybrid, you can get very, very accurate results. So for example, what is shown here is if you do pure database analytics, you get 80% accuracy of your predictive analytics using digital twins, right? Which is what most of the industry uses. If you did simulation-based digital twins, then you get 90% accuracy. But when you combine it with the hybrid, then you get 98 to 99%. This is the kind of work that we are working with customers such as Flowserve and other industrial flow networks, and it's been really, really disruptive in the industry. I kind of mentioned the area of multiphysics simulation when I showed the broad overview. This is showing the detail as to how we are creating a platform called ENID that is essentially allowing our customers to build entire solutions, right, using multiphysics. So each of the products that we have, Fluent, HFSS, Maxwell, etc., right, we are providing through the right modern APIs, right? Essentially think of it as creating microservices that will run on the cloud, right? So each of those products are having these modern APIs. Then we are building out entire sort of solutions, right? Tying these modern APIs, right, to build entire solutions such as autonomy solutions, such as 5G, electrification, and so on, or electric powertrain or electronic systems design. So this is essentially a very, very exciting area. And as I said, this platform allows us to do multi-physics, multi-scale, multi-domain simulation. Another work that we are doing on the platform is our Minerva platform, which is our simulation data platform. Now, what this platform allows us to do is to essentially take simulation, right? And people in our industry do a lot of simulation, right? And as they're doing this simulation for mechanical simulation, for fluid simulation, they're generating a lot of data. And when they're doing this, they're doing it to do sort of different optimization, right? They have a part, the part can be 4-inch long or 5-inch long or 6-inch long, right? They'll do thousands of simulations to get to the most optimal design. So as people are doing these different optimizations, right, it's generating a lot of data. So we have an entire platform called Minerva, which allows the customer to do this simulation process and data management. And this today runs on premise, but we are working on technology that will take it to the cloud. So that will truly allow collaboration among different engineers, right, in different geographies on the cloud to share and collaborate on simulation data and data platforms. We also talked about a materials platform called Granta, right, that we had acquired in 2019. What we have done is essentially each of our solvers are driven with different materials properties, like the Young's modulus of steel or the Reynolds number for fluids and so on, right? In the past, those parameters, characteristics were programmed into the solvers. Now, through our Granta platform, our materials data connectivity, we can actually connect hundreds of thousands of different materials properties into these different solvers. So our materials intelligence platform is working hand in hand with this Minerva platform for simulation data. And then this platform that we have ties to PLM, provides PLM and ERP interoperability and runs on the cloud, on-premise, private clouds, as well as hybrid clouds. And essentially, this is allowing us to connect physics with data. That brings me to this very, very exciting area of model-based systems engineering, right? In the industry like aerospace and automotive and so on, people have been talking about model-based systems engineering for a while, right? But when people do MBSE, they only talk about the system level models, right? Using languages like SysML and so on. But what we are doing at Ansys is to tie those system level models with the 3D simulation, right, which is shown at the bottom right. So suppose you are designing a part, right, an airplane engine, you can specify the requirement of the airplane engine in a high level language like SysML. But then people do hundreds of thousands of different designs of that airplane engine for different parameters. Then for each of those designs, right, you can actually have an implementation with a CAD tool and then through a simulation with 3D simulation. And then you can run the verification through Ansys Mechanical or Fluent or whatever. What we are doing with this model-based systems engineering is to provide that seamless connection from the high level to the low level. So this is allowing us to do this particular vision, which I want to end my presentation with, right? So people have been always essentially in the world of sort of product innovation, people imagine a product, then a prototype a product sort of in the hardware world, and then they do a virtual prototyping, right? So this has been the vision for many, many years, right? So people in this industry talk about what is called this V cycle, right? Which is you start with a specification and essentially you do a certain design, and much of the cost of this component, right, of this asset, like an airplane or a chip or a engine, is determined upfront, right? And essentially, and the freedom to innovate pretty much goes in the life cycle, right? You make some initial choices, and that's where things are stuck, right? So essentially, in the V cycle, what happens? You start with some requirements, you immediately go to subsystem level design, component level design, right? And you do the CAD models and simulations, which is where Ansys comes in. And then you go to the right part of the V cycle and you do final validation. You've built your motor or design or whatever. But the question we ask is, if you are able to tie in, right, to do very accurate physics-based simulation in the upfront, right? Essentially, you can do rapid prototyping. And suppose you find out that there is a wrong design that you did, you have a possibility of changing the design. So essentially, we're moving that cost curve. As I showed, the earlier cost curve was the top curve. Now we can push the cost curve down, right? And the innovation, it was here, the innovation goes to the top, right? The freedom to be. This is the vision of rapid prototyping, virtual validation. So let me kind of illustrate that with an example, and that will be my last slide, right? So people are talking about electric vehicle design, right? I mean, you want to drive a Tesla, right? To drive a Tesla, the Tesla has sort of more software than hardware, right? People talk of Tesla as a car on wheels, as electronics on wheels. So essentially, in electric vehicle design, right, you are dealing with some battery systems, you're dealing with electric motors, you're dealing with powertrain and so on. So you have the hardware of that design, right? And then you have the software of the design. And typically in the industry, people use low fidelity models, right? When they are doing this initial design, right? So you do a low fidelity model of your motor, low fidelity model of its controller, the software controller, and you try to do this motor, and then you have to actually test that motor, right? You actually put that motor in a component test rig. This is what's called hardware-based prototyping. Then you take the motor and you stick it with some battery systems and so on, powertrains, and then again, you essentially people use low fidelity models, right? Then you are supposed to test this physical powertrain with a motor and battery, right? And then you do some more testing. Then you take that whole thing, put it in a car, and you do the testing on the car. In this way, right, suppose you make some wrong choices of the design of the electric motor, whatever, you cannot actually go back to the new design because you have made too much sort of progress in this area. The new way of rapid prototyping is saying, if you could do a high fidelity simulation, right, upfront, right? And the reason you can do high fidelity is because of the technology I talked about, right, with AI, ML, and HPC and so on, right? Essentially, we are allowing with this vision, right, with this sort of MBSE vision with the system level, SysML, and so on, and essentially tying that with very fast but accurate high fidelity simulation, we are enabling our customers to get to virtual validation and rapid prototyping. This is what I wanted to end my presentation with. I want to thank you all for attending my presentation. Simulation, as you know, is the center of virtual prototyping. And people are moving, all our customers are moving from hardware prototyping and testing to software prototyping and validation and verification, which is sort of where I ended my presentation with. This is allowing our customers to do much more rapid innovation, lowering the cycle time, lowering risk, and increasing quality. And Ansys, as I'm sure you know, right, we provide the broadest and the deepest simulation platform in the industry with leading physics solvers, as well as this ability to do this multi-physics, multi-domain, multi-scale simulation. Thank you very much for your attention.